Alright, hello everyone, welcome back to the second video on the Chem Mega channel, and right now I'm just going to go over all the things I think you need to know for tomorrow's thermochemistry test. And we're going to start by going over what state functions are. So state functions, as you can see on the screen, are properties that do not depend on what happened to the substance prior. So anything could have happened to the substance, however it was prepared, and it will still get to the same place as measured in a state function. So changes in state functions are also important, since they only depend on the final and initial states of whatever the property is. So think of all your delta state functions, so like delta H, delta T, so temperature and enthalpy would be examples of state functions. And this idea can kind of be tied into Hess's law, since in Hess's law you can have multiple different reactions. So basically, you can have multiple different reactions, and that will have the same delta H value as, say, a reaction with the same products and reactants, but only in one step. So basically, the idea is that you can have the same enthalpy change for a one-step reaction as if you broke that process up into multiple steps. So state functions in general are just kind of a general category of properties, and in this case, enthalpy is the example that we'll be focusing on. So next, we'll be going over some of the common heat ofs that you'll be seeing on tomorrow's test. So one of the most ones that we recently learned is the heat of formation, as you can see with this symbol. So delta H, this little circle here, and F. So delta H obviously is change in enthalpy, and in general, the heat of formation is the amount of energy or heat needed to form 1 mole of a substance. So the circle here, that basically indicates the conditions at which you're taking delta H. So specifically, it's at 25 degrees Celsius, 1 atm, and it's at 1 mole of the substance. So that's what this says here, and F is just for formation. So heat of fusion, as we kind of learned at the beginning of the year, is the amount of energy needed to melt a substance. Usually we think of it in terms of joules per gram, and in that case, like for water, the heat of fusion would be 334 joules per gram. And it's kind of similar with the heat of vaporization, which is 2,260 joules per gram. So it's the amount of energy needed to vaporize a substance. So those are just kind of the heats. And now we'll be getting into Hess's law. So I'm just going to kind of walk you through this practice problem that I put up here, and you'll hopefully get a better sense of how to go about this type of problem. So you're given these three thermochemical equations, and you're trying to find a delta H value for the decomposition of 1 mole of C2H2 to their elements in their stable state at 25 degrees Celsius and 1 atm. So as you can see here, they're already the standard conditions I talked about earlier with the heat of formation. So I think the first thing that you should try to do is find out where you're trying to get to and where you're trying to get from. So in other words, find the final products and final reactants of what you're trying to get. So that's what I've written over here. So C2H2 yields 2C plus H2. So kind of something with those elements in those places. Obviously, the coefficient can change depending on what we actually end up with. So knowing that you have to start with C2H2, the first equation that you probably want to start with is this one, which has C2H2 on the left. So you're going to write that over here, this whole equation out here. So now you know that you have 2CO2 and H2O. And since the question said that you're supposed to get the C2H2 to the elements, you know that you can only have carbon and hydrogen in your final equation. So that means you'll have to eliminate both carbon dioxide and water. So the first step would be to find out how to get rid of those. So in order to do that, you would have to flip both of these equations so that basically this would yield carbon dioxide as a product, which would then be used in this reaction to form carbon and oxygen. So that's how you would know to flip these two. But then you still have to figure out what coefficient to multiply them so you can effectively cancel everything out. So the first thing you would do is flip that, write it down. So as you can see here, with these two equations here, and you know that you have 2 moles of carbon dioxide here, so you would multiply this entire equation by 2 to cancel out the carbon dioxides, which would give you 2C and 2O2. And you would also have to multiply the delta H value that you had here by 2. And notice that the sign changed here because we flipped the equation. And you're going to do something similar with water. Since this is 1 mole here, you also have 1 mole here, so that's basically the same as this equation here, but flipped. So that yields 2 carbon and 1 hydrogen, and again, the delta H value here would be flipped. So now as you can see here, if we try to cancel everything out, you'll notice that the carbon dioxides cancel out, the waters cancel out, and the oxygens cancel out. But anyways, the idea is that everything cancels out, and you're left with this formula at the bottom, and you have to add up all your delta H values to get the final one, which is negative 226.7 kilojoules. So moving on to the last thing we're going to cover, and that's basically how to read an energy diagram. So as you can see here, the x-axis is always the reaction path, and the y-axis is always your enthalpy with the appropriate unit. So one of the things that you would be finding here is your delta H value, your activation energy for the reverse reaction, and whether the reaction as a whole is endothermic or exothermic. So here you would notice that basically if it starts low and ends high, it's endothermic since it's gaining and absorbing energy. So that's the first thing you would see. If you want delta H, you would do the final amount of enthalpy minus the initial, so that would be 100 minus 10 or 90 kilojoules. If you want the forward activation energy, you would go the highest point in the graph minus the lowest point, so that would be 110 kilojoules. And if you want it for the reverse reaction, imagine just kind of this graph flipped here, and it's just this minus this, since it would start here and the highest would be here, so you would do 120 minus 100 or 20 kilojoules. So that's the activation energy for the reverse reaction. And that's pretty much it for thermochemistry. Hopefully you're studying for the test and you can do more practice problems on the Megadoc, which hopefully should be pretty difficult, unless you're really good, in which case they probably aren't. But anyways, thanks for watching.